Caitlin's in the waiting room. You've got 8.
Okay.
Missing a Marcus and a Sophie.
Yeah, probably.
Everything's good on YouTube. I'm going to log out.
Thank you.
On YouTube just in case.
Okay, test, test. Can you hear me?
All good.
Awesome.
Fair warning, everybody. We're already live on YouTube, so wave to the fans. All right. Marcus is in the waiting room, so you got 8 waiting. All right, just waiting for the last few of our people, our panel, our team to get here, and then we'll get started.
Francesco is, yeah, he's coming.
Okay.
I guess if you can follow directions, he's coming.
Okay. Glenn too. Apparently the link I emailed you guys was no good, which is my bad.
Yeah, I had to enter in the meeting ID and the password. So
sorry about that. Hopefully
minor
the next one works.
inconvenience.
Minor inconvenience. Hopefully the next one works.
Yeah.
I don't know why it happened. I copied them all the same, so maybe I just, missed a letter or something. Who knows? Our plan is to disable the rights to unmute yourself while everyone is in here while the video is playing. Glenn's here. So I will disable that, and then I will ask everyone to leave their cameras off. That way we don't have any problems with buffering speed. And we can, Sophie's in the waiting room, Federico. And that way we can make sure that that video plays cleanly. And then Debica will take care of the questioning and making sure that we stay on time for that. And the live stream is going already on YouTube. Hey, Glenn, you found us. And Kim's taking care of monitoring that YouTube live chat, which is much appreciated. All right, you've got 10 waiting, so I think that sounds like a team there, Federico. Let's wait and see if we get an executive director, and then we will go ahead and let them in and get started. Everyone doing okay today? Good.
Moving day.
Moving day. Yeah, it's a little rainy here in Houston. Moving day doesn't sound like a whole lot of fun.
Not a lot of.
Glenn, we can't hear you, but you have random parts of things. Is that a pop gun? You have. Fusco.
So I bought a 3D printer, and because I could not buy a model, and see, I can buy models of different engines, but I can't buy a model of a transmission for a car. I bought the 3D printer so I could make my own transmission as a model. Isn't that neat? And I'm almost done with all the print. There's only 55 parts. So.
But if you're, it's not an internal combustion engine, because I'm thinking the plastic would melt.
So, right. So for my kids to get to learn to drive, they had to build a plastic model engine so that they understood something about cars, right?
Okay.
And I've always wanted to have a transmission because, let's face it, that I just never understood how a transmission worked. It's very complicated. And so I looked all over and could not buy a transmission plastic model kit for my kids to learn. But on Thingiverse, people have made lots of different plastic transmissions that you can assemble once you print it. So that's what I'm doing. Anyway, something fun to do. And it's only 55 parts. So there.
55. All right. Well, I hope that everybody watching us live on YouTube enjoyed that. You can 3D print your own transmission if you get a 3D printer. It's only 55 parts. Okay. I am going to let our team in. The first team to present today is Prometheus. Once I let them in, we are going to ask that everybody keeps their cameras off so that we can get the video cleanly presented without any buffering speed issues. I will also remove your rights to unmute yourself for the first 25 minutes as the video presents. That way we don't have, again, any issues with audio. So let me let these kids in, and I will repeat myself one more time. And then we'll get started. Good morning, Team Prometheus. Welcome to your final project presentation. We do have our board of directors here. Your mentor is already here, and we are currently already live streaming on YouTube, so wave to the fans. We are going to go ahead and get started with your presentation. I told you guys about 5 minutes for us to get settled in, and that's exactly what we got here. So what I'm going to ask is that you guys go ahead and turn off your videos so that we don't have any problem with buffering speed. And then I'm going to remove your ability to unmute yourselves so that we don't have any issues with audio. So just give me 1 minute here. I do have your video ready to play, and we will get started. All right, here we go.
Good morning, this is Team Prometheus, and we're going to talk about our mission towards you. Those are the main contents we're going to focus on. We have the mission outline, mining, crew health, space law, and budget plan. Just to give you a general idea of what we're going to discuss inside of this PowerPoint. We're going to mine you when to bring in our in-situ resource utilization of the minerals and the materials that we're going to extract from it. 4 astronauts are going to land on its surface together with mining tools, and they're going to extract water, ammonia, nickel, iron, and cobalt. We have more or less estimated a budget plan, which is about $1.6 billion. Well, this is a sort of identity card of the asteroid, a Yuga, which we're going actually to mine to land on it. But the most important feature that I want to underline is actually the Hayabusa 2 mission, which is a JAXA mission who has already landed on its surface in 2018, and it's planning on bringing samples back from it on Earth the end of December of the current year. This is, of course, really important because it means that Yuga is an asteroid that we can land on, and we can carry on with further exploration of it.
First of all, we want to look on a very important topic of our mission, the objectives. We have many 3 objectives. The first one is we want to create a gateway and a launch site for further space missions. We want to resupply Earth with vital resources, for example, cobalt, and we want to study more about the early age of our solar system and also the origin of our Earth. For realizing this project, we will send 4 astronauts with a duration of 8 months on the 2nd January of the year 2034. Before we start with our manned mission, we need to be sure that we know all details about Yuga. Therefore, Prometheus will send a research mission, and it will look similar to the Hayabusa 2. This spacecraft will mainly focus on determining the composition of Yuga, determining the seasonal temperature, and it will deliver solar panels so that we can make sure we have enough energy sources for our manned mission. Next one, why do we want to mine Yuga? Why we are especially focusing on this asteroid? Yuga is a near Earth object, which means that it's very close to the Earth. It has a minimum orbital intersection distance of about 95,400 kilometers. And the resources on the asteroid can be used for in-situ resource utilizations, which makes us possible to start further space missions from Yuga. The room temperatures in winter, all resources in the small distance to Earth makes us possible to land, study, and to mine the asteroid. Small bodies like asteroids and comets are time capsules which contain information about the history of our solar system and of the Earth. So by mining the asteroid, we can learn more about our history and about the history of our Earth. And finally, we can take back valuable resources such as cobalt to use them here on Earth. Our landing site will be one of the poles. Whether it is the North Pole or the South Pole, we have to decide after our research mission, because our research mission will decide whether there is winter or summer on one of the poles. We plan to land there on winter because on winter we will have about room temperatures, which is optimal for our tools, machines, and for our crew. On the poles, we have a higher chance of finding water, and to increase this chance, we will land in the inner circle of the poles.
For power, we plan to use a multiple mission radioisotope thermoelectric generator. Usually the radioisotope we would use would be plutonium-238. This would be used to produce heat. The MMRTG produces electricity through the heat emitted by the plutonium. The advantage of this would be is that MMRTG are not dependent on radiation, temperature, or light. They also produce power for a long period of time, as shown by the Pioneer 10 and 11 missions, which continued operating for close to 3 decades. There's also a reduced risk with this technology as it's pre-existing. For solar energy, Ryugu varies between 0.96 and 1.41 astronomical units for the sun. Therefore, solar panels are a viable option. The spider water extraction system for mining uses deployable solar panels to generate electrical energy for mining and making steam to extract volatiles. The solar panels are attached to the system itself. Crew Health also used solar panels for the Eclipse habitat, using an origami folding solar array which we set up on the surface in the 2004 research mission. Drills will be used to keep the solar panels in place. The advantage of this is that it is lightweight, compact, foldable, and cost-effective with no astronaut assembly required. Mining. Resources and in-situ resource utilization. We are mining water for growing plants and integration to radiation shielding, ammonia for plant fertilizer and water disinfection, nickel and iron for manufacturing tools and structures, cobalt for selling resources on Earth.
Water is with no doubt one of the most important resources that we're going to extract from Ryugu's surface. But we have one problem with water. A Yabusa 2 mission from JAXA has shown that there is less water than it was expected to be on the asteroid surface. This means that we cannot rely on water to refuel the spacecraft for the combat voyage towards Earth, but we'd rather use water for growing plants and to sustain the astronauts' life on the asteroid. Other two important resources are actually ammonia and cobalt. Cobalt is the only one that we're going to bring back on Earth, while ammonia is going to be extracted by the spider water extraction system, has water also. And it's going to be used actually as fertilizer for plants and also to purify water supplies. In the end, we have nickel and iron, which are together with cobalt, three elements that are going to be extracted, actually scraped off the asteroid surface thanks to the scraper that we have personally designed. And they're going then to be turned to very high periodic metals thanks to the MON process, which is a chemical process.
To extract water and other volatiles from Ryugu, we will be using Honeybee Robotics' spider water extraction system. The spider is a robot equipped with flexible legs and deep-fluted drills, which point inwards at an angle. The spider's legs allow it to firstly anchor itself to an asteroid, extract volatiles from a sample, and then reposition itself by repositioning its drills or by hopping using steam propulsion from the water it's extracted. This process will be continuously repeated, and the spider will be able to do this from using deployable solar panels and also RTG. The RTG will assist in areas of little to no sunlight and also provide heat for heating the sample and extracting the volatiles. The spider will achieve extraction of water and other volatiles by using a coring drill, which is heated on the inside. The drills are firstly deployed, capturing a sample, and are then heated, causing volatiles to move up the drill. Eventually, they will reach a cold finger in which they will condense and can then be extracted and used. What makes the spider advantageous as compared to traditional mining techniques is that the feedstock is both mined and extracted by the same system. This approach reduces the need for significant surface assets or the energy intensiveness that would be required if the feedstock was then mined, then transported, and then processed. To obtain non-volatile resources, we will use a scraper like the one shown in the animation. It will use an anchoring drill on the back, which it will deploy to stop any reactionary forces from scraping, pushing it off the asteroid. It will then place rocks into a container and then transport it to the mining facility for further processing. Because there hasn't been too much technology devoted to asteroid scraping, we've based our technology off Mars rover Perseverance, the 6 wheels allowing it to turn a full 360 degrees on a point. As our technology for asteroid mining becomes more and more advanced, our designs will surely change, but a scraper for an asteroid like Ryugu will definitely be useful considering it's a rubble pile asteroid and consists of a collection of easily scrapable rocks.
Processing the mining material. Generally, only the basic ore processing will take place on the asteroid, the rest on Earth. The ore will be ground up and sifted into different sizes. Then, vibrating screens will be used to shift the grains. Then the material will be crushed in small gravity using centrifugal movement, and the nickel iron metal granulates will be separated from the silicate grails.
For processing this mining material, we will mainly need 2 tools. The first one is a centrifugal grinder and the second one is a solar oven. The solar oven is used to cook out volatiles, and the centrifugal grinder works like a spinning wheel which accelerates materials down its spokes and flings it again against an impact block.
Crew health. Since this mission is so far into the future, it is hard to know the exact type of spacesuit that we would want to use. However, it is likely to be very similar to the prototype exploration suits. This is because it has a suit control assembly box on the front that allows the wearer to adjust their life support components such as cooling and pressure. This would be used for EVAs as it has good mobility and visibility. Furthermore, the suit has certain parts that can be 3D printed so that the size can be adjusted for comfort, safety, and mobility. The crew would wear suits that are made of yarn with boron nitride nanotubes woven into them because their radiation dosage needs to be kept to a minimum. These would be worn underneath their spacesuits when they are outside the habitat. They would also be required to have personal dosimeters. An inflatable habitat made of Vectran, an anti-radiation fabric, similar to that produced by Bigelow Aerospace, would be used on the surface. We decided to choose an inflatable habitat instead of 3D printing one, as there is not much regolith on the surface of Ryugu. We would have had to use the materials we would be extracting to build the habitat. An inflatable habitat is much more feasible in this case. The crew habitat will be based on 2 models made by Bigelow Aerospace, the Sundancer and the B330. These are only being used as examples for preliminary planning as they showcase the technology we would want to use for our mission in the distant future. The proposed habitat will have 4 crew members and will be powered by solar panels. We have found out that the temperature on the asteroid changes based on where it is relative to the sun. Fortunately, in the winter, the surface temperature averages around room temperature. So as long as our habitat is in the hemisphere where it is winter at the time, the crew shouldn't be exposed to uncomfortably high temperatures. Also, the thermal inertia of the asteroid is quite high, so the temperature change they experience won't be sudden. It is important that the crew's mental well-being is tracked, as they will be in isolation from the world for several months. To help improve their mental health, we plan to give them regular psychological tests and checkups with a therapist, frequent contact with family and friends, including video messages, the opportunity to acquire a new skill, for example, learning a new language, a schedule to work from including times for breaks and relaxation, and some specially requested food that will be brought with them for when they need to feel at home. We are also planning to have a small amount of plants growing to allow them to feel closer to nature.
Water recovery system is another essential piece of equipment for crew health. It's currently used on the International Space Station and recycles up to 93% of water brought with them. This saves about 18,143 litres per year. It processes wastewater such as urine into potable water for the crew to use. The oxygen generation system and the Russian electron splits water into its components of oxygen and hydrogen by electrolysis. The oxygen produced can be released into the cabin for the crew to breathe, and the hydrogen is fed into the Sabatier system, which we'll speak about later. The process is capable of producing up to 9 kg of oxygen for the crew per day, and the electricity required by the electrolysis can be provided by solar panels. Sabatier system. This uses waste carbon dioxide produced by the crew, as well as the waste hydrogen from the oxygen generation system to produce both water and methane. It produces about 2,006 litres of water per year, and that can be used as potable water for the crew, or it can be split into its components for oxygen. The methane can then be used as a potential rocket propellant, or it can be vented into space, which is often done by the International Space Station. Waste disposal. The toilet must be compact in order to maximise available volume for both equipment and for the comfort of the crew. The heat melt compactor compacts waste into 9-inch square tiles. The compacted waste is then heated to 150 degrees in order to sterilize the material, boil off water, and vent off gases. The steam can be reclaimed by the water recovery system. The gases can either be vented into space or processed into safe gases, and the tiles can be used as a radiation shielding. Physical health and exercise. The Rocky is a compact piece of exercise equipment which they are going to be using for the Orion missions. Features of Rocky include a rowing machine for aerobic exercise and cardiovascular health. It is loaded with 400 pounds of weight which can be used for strength training and has a variety of handles depending on what type of exercise you'd like to take part in. Resistance bands are also feasible but must be stronger than those typically used on Earth, and therefore more development must be done to create suitable resistance bands for our mission.
So let's talk about nutrition. Why is it so important to give the crew good nutrition? During the day, the crew members we have to manage the mining station, repair mining tools, do their daily physical activities, work, and study. All of this requires energy. This is why the crew will have 3 healthy meals a day in order to be at its best. Microgravity has really bad effects on the human body. This is why a good nutrient, mineral, and vitamin intake is required to prevent and reduce the bad effects of microgravity. Finally, we often forget it, but food is actually a huge part of the psychological state and the morale of the crew. A good meal can make you remind your family, motivate you to work. Of course, we will allow the crew members to personalize their own dish so that they can eat what they like, and to bring also their recipes from home. Of course, adapted to microgravity. Now, how to feed the crew? Feeding the crew will be almost the same as feeding the ISS astronauts. Food must follow specific criteria in order to eat safely in microgravity. For instance, it mustn't make crumbs or be too heavy. It also has to be very tasty. Indeed, microgravity affects fluid shift, which occurs a loss of taste. So spicy and well-seasoned food are welcome. Now, what will the crew eat? Here are the forms of food that the crew may eat. The most useful ones are dehydrated and freeze-dried food, because you just have to add water, water that you can get thanks to the Eclipse and the water recovery system. One astronaut has 3 meals a day and a collation, which represent about 2.5 kilograms of food per day per astronaut. To fight microgravity effects on the organism, we also plan to give the crew, in addition to their daily meals, a complement pill containing omega-3 for cardiovascular problems, vitamins for bone loss, eyeballs elongation, etc. And for gastrointestinal problems, we plan to add in the food of the crew some prebiotics and probiotics.
Astronauts will train in a simulated microgravity environment to ensure that they can safely operate, set up and repair the equipment as necessary. It is likely that crude elements on the surface will operate similarly to the International Space Station due to low gravity, and training will therefore be similar to that for these missions. This will include the use of robotic arms and handrails alongside a tether to the habitat. A safer pack will be attached to the spacesuit for emergencies, and EVA equipment will be designed to allow the astronauts to live and operate safely on the surface of the asteroid. A flight surgeon will be present as part of the crew and will be able to assist with any medical issues that arise alongside monitoring the health of the astronauts before and during the mission. Crew members will also be given paramedic training in order to provide emergency medical support, as is typical for crewed missions. Standard medication and first aid supplies will be provided to the crew, including treatment for space motion sickness, which is experienced by many astronauts during the early stages of spaceflight. The use of space must be in the interest of all countries. Therefore, it is important that any significant discoveries made, such as unexpected minerals or evidence of life, are shared, as profit must be independent of scientific advancement. It would be important to clarify that in national and international law tools for liability for materials that are returned to Earth, and to prevent liability issues should the facilities be used by another space agency for future missions. Whilst mining the asteroid, the crew must be careful not to contaminate the surface or cause significant damage to the asteroid. It may also be necessary to redefine the laws of preservation of celestial bodies before the mission. Sovereignty of a celestial body cannot be claimed for any reason. However, it is possible to claim a base of operations and therefore possible to set up a mining facility on the surface of an asteroid. The Moon Treaty prevents the exploitation or ownership of natural resources from space, which would make mining an asteroid illegal. However, this treaty was not signed by several nations, including the United States, United Kingdom, China, Japan, and Luxembourg. Therefore, provided that all nations involved in the launch haven't signed the treaty, the mining mission will be unaffected. Due to the conflict between nations regarding the acceptance of the Moon Treaty and its application in national space law, it is likely that new international laws regarding mining would have to be agreed upon prior to the launch.
Hello everyone, this is Curtis from Team Prometheus. We'll be speaking about our budget plan, our primary source of income for the mission, and also our target industries, our potential target industries for selling our product from mining. So our primary source of income for the mission is going to be by funding from member states of the mission. As this mission is going to be a multinational project, because a single state will not be able to fund the entire mission and also to supply the mission with necessary technologies. Therefore, governments of the member states will provide financial aid, and also we plan on opening the opportunity for private investors and stakeholders to invest on our mission to gain the profit. And we are also planning on conducting research activities on the asteroid for research institutions and universities which are interested in asteroid Ryugu, and we'll also bring back soil samples to say for these institutions. Our main target for selling our product is going to be tech industries which are involved in manufacturing mobile phones and computers, because cobalt is one of the main materials required in making rechargeable batteries. Therefore, companies like Samsung, Apple, Dell will require cobalt to make rechargeable battery for their device. Therefore, they will be our target market. And also, automotive industries will also require a rechargeable batteries. Therefore, they are also going to be our potential target. Also, industries involved in production of glass and ceramics are also our target industries. We also plan on selling the product, on selling cobalt to metal industries which are involved in the production of metal products and alloys. Therefore, they will require cobalt, and we'll be able to provide that to them. And we also plan on holding an important role in investment sectors such as cobalt future and cobalt stake to gain profits. That will be it for me. Thank you.
Here's a brief overview for all of our costs for this mission. You can see that our life support system is the most expensive out of all of them. The power sources, habitat, and mining systems are also quite expensive, but we plan on leaving these systems on the asteroid, and therefore these costs will not be included in the future missions. Then we move on to risk management. We want our total mission risk to be extremely low. This gives us a much higher confidence that our mission will succeed. I want to focus on points 1 and 3, 1 being the Hayabusa 2 spacecraft, which proved that this has been done before, so we are not moving into unknown territory when we want to land on the asteroid. And then point 3 being our life support system is extremely reliable, and this is a well understood system, so the risk of something failing on that system is decreased. The health and safety of our astronauts is extremely important on this mission. Profit is extremely important in any business scenario. This graph visually shows us the estimated profit based on mission and mining costs. We can see that our mission cost is extremely high, with our profit being extremely low. And this is expected in our first mission. We expect making little to no profit as we are launching our most expensive and also our most necessary equipment first, so that the future missions do not have to deal with this issue and they can simply focus on making profit. I would much rather look at this graph simply because the values look much better. One thing that you should notice is that our mission should not be focused on in the short term, but rather in the long term. With each mission, you can see that our total mission cost decreases over time. With each mission to the asteroid, we plan on taking more mining equipment to make our mining setup much more efficient so that it can extract more minerals and metals. And from this, we can see that our profit increases exponentially over time. And this proves that our mission can be profitable in the long term. Lastly, our starting budget of 1.6 billion is quite large, but we are willing to pay that cost to ensure the safety and comfort of our astronauts. We have proven that our mission is profitable in the long term. We have kept our risks and expenses to a minimum. With this mission, we do not only focus on being profitable with the amount of metals that we mine, but also with the amount of knowledge and information that we gain from this.
Our team consists of members from all over the world, and that is why we think that global collaboration is extremely important in this mission. And I think that answers the question of why investors should invest in our mission and our goal.
All right, all. So that is the conclusion of the main presentation. So I'd like to open it up to our panel for questions. So I'll go ahead and call on Francesco first, and then we'll cycle through the other members that are in attendance.
And at this time, team, if you would like to turn your cameras on, you are welcome to.
Hello, Team Prometheus. And first of all, good job on the slides. They were clear. The design was pleasing to the eye. You really enjoyed going through. And also your presentation was done very well. One thing important, I'd like you to expand a little bit on it, since you are here to convince us to invest money in your project, is I want a little better understanding of this long-term profit. With $28 per kilograms on cobalt as your only clear source of income, I would like to see how you see in the long term this is going to bring profit to the project. And in particular, there's some things that I need to understand better, like, for example, your spider water extraction tool. It seems like a big investment for asteroids where yourself say that there might be very little water, if any at all. And that cost, I don't see the breakdown. Like you're talking, you do training on microgravity, which means using the International Space Station. That's besides the operational, it's going to might be very expensive. I want to see if you guys took that into account when you estimated your cost. So basically someone that explained how you plan that long-term profit, and if you really look at every single thing to reduce your initial cost.
So Marcus, why don't you start us off since you presented the business plan, and then you can hand it off to other members of your team to help you out.
Sure. Give me a moment to think. So the $28 per kilogram is, I want to say, quite low, but that's almost, like I mentioned in the slides, our most valuable material. So I want to say long-term as in, long-term, not very, I want to say short long-term, it's rather long-term, if that makes any sense. But how do I, that is of most clear source of income, I want to say, that is true. But I think our other sources of income are also, how can I say, what's the word for it in English? I can say that will also benefit us. I think that is possible with other sources of income. It's not so, I want to say, far-fetched. So that will also bring it into account. And I think just in general, if you start any mining business, the overall goal is not to go into debt, although many do. But I think even if you go into space, I think your things have to be a little bit more laid out. And I think that ours is profitable in the long term. Yeah.
So do you expect that the cost of cobalt will go up?
Let's say that, I mean, the minerals on Earth are getting less. So if we focus on, again, that long term, the cost will go up simply because the Earth minerals are getting less. So in that long term, the cost will eventually go up. It might go down again, but I want to say any stock that started low is quite high now. So I want to say for our mission time and that launch window, the price might be higher or it might be lower, but I think it will be higher just because any stock goes up over time. But and I think also investors should focus on that this, I think anybody will be interested in any mineral or metal that's mined elsewhere than Earth. So if you say this metal is mined on another planet or an asteroid, I think anybody will be quite interested in that metal, just in general. I don't know if that answers your question.
Okay, and then moving on to the spider drill. Francesco asked for a clarification on that.
Yeah.
Yes, I can answer. Oh, sorry. Yeah, Joe, you can also
I don't
help
mind.
me.
We could both answer. So I think the value in the spider drill is just that water on a extraterrestrial, on a celestial body somewhere else is so valuable because, it can be used for fuel. It sustains the life on the asteroid, and it's even if there was a very small amount of water, the ammonia could be used still for other purposes. So I think that's why we would invest quite a lot of money into it.
Yeah, furthermore, for what concerns the amount of water that Ryugu is provided with, we'll still have to look deeper into that. That's the reason why we're also sending an forerunner mission, the one that will go deeper into the asteroid composition, which will include also studying deeper the amount of water present on the asteroid, and also as we said in the presentation, what concerns the temperature. So of course, the real amount of water that we are expecting to have is not certain yet, but we'll have further points on that later on after the first mission that we're projecting to do.
And just to close up, so you guys believe that the data that now you have from the JAXA are not correct, or you hope they're not correct? I mean, I'm trying to see what's the idea of finding the water there.
No, it's rather than the JAXA is not providing a percentage of amount of water that we have on the asteroid, so we don't have already a precise amount of that. We rather just have the fact that there is less water than it was expected to be on the asteroid, but we don't have a specific number which can quantify the amount of that.
Okay, that answered my question.
Very good. I also have a question about the spider drills, if that's okay. So on the spider drills, you've got several drills that are going at an angle and they're in opposition to each other. Is this going to be a problem? How many spider drill components can you lose before you're no longer able to use it? And part of what I'm thinking of is that if I lose one of them, then that means that the other one is not going to be able to go in, and you're running a risk of it floating away from the asteroid just from its injection. Is there a plan for being able to refurbish and repair this kind of a drill?
So I guess so. The spider drill has eight legs and it has 8 drills on it. And from reading like other documentation from Honeybee Robotics, so they have this other thing called a PVEX drill, and the idea they're trying to get across was that you don't want to put all your eggs in one basket. So I think that's why you wouldn't have one massive drill. Instead, I'm not sure to the amount of how many of them could fail until the whole system would fail, but I'm pretty sure it would be a fair few could fail before it can't actually stay on the asteroid anymore.
Okay.
Yeah, if anyone else wants to add anything.
I think we're
Good
good.
comment.
Okay, Rob, I think you had a question ready.
Yeah, I sure do. So you've got iron and nickel and cobalt, but you're just selling the cobalt. What is the business plan of what you're going to do with the iron and nickel?
The main purpose was to use nickel and iron for manufacturing. So that's the profit will be, and not bringing manufacturing tools from Earth, rather to 3D print or produce them directly on the asteroid. So that's how we're going to get a profit from that.
Okay. And the research mission that you're sending out beforehand, did you have any estimate of the cost of that mission? I think you said it was 1.6 billion budget investment at the beginning. How much of that is this research mission?
I would like to answer this question. It would be about $150 million.
Okay. Okay, Alex, you have any questions?
Yeah, I did have a question. Going back to the budget, looking at these graphs, so it kind of touches on Francesco's question about the price of cobalt going up. How do we know the price of cobalt would go up? And if you're bringing back so much cobalt, how do we know it would continue to go up even though the supply of cobalt is increasing?
I'll answer that. Also, I mean, the amount of cobalt that we will bring back, we're unsure of. But I think that's when we are on the asteroid and deploy the mining systems. I think the astronauts will, you know, take information from everything, see how much we can extract. So if we say we bring back a lot, we obviously have a lot of cobalt coming to Earth. So honestly, the price, we never know when it's going to go up or down. We can make a good estimate whether it is going to go up or down. But yeah, I think in general, you always hope it goes up, but the chance of it is always going down. But I mean, again, going back to any mineral or metal that is mined on an asteroid seems to be extremely valuable for anybody interested or just anybody in general.
In addition to that, if we're going to sell cobalt, the $28 per kilogram of value of cobalt is not, it's an estimation or it's an average value. It might increase in some markets and it might decrease in some markets. The small fraction increase in some markets will bring us a high amount of profit when we increase the mass of the product that we're going to sell. And when we sell our product, our cobalt, slowly in time to time, by not putting it all at the same time in the market, we can control that. We can make sure that the demand of cobalt will not decrease drastically, but when we bring the cobalt, and also we can control the market to our favor.
Okay, let me ask a non-budget question. How you think, what's your rationale basically to comply with Article 1 of the Outer Space Treaty? In theory, why do you think that your mission is benefiting the interests of all countries?
I can get on. I think that it would benefit all countries, as part of our mission is to leave a long-term station, so any future space missions can be launched from the asteroid, like as a stop-off point. And also we're hoping to find any evidence of life or prehistoric rocks, as the asteroid is fairly old.
Francesco, did that answer your question?
That answered my question, yes.
Yeah. Okay, I got a question. And you should have expected this one. It's the radiation shielding question. I heard one mention of a radiation shielding in there that you were going to add through time. What is your plan to deal with radiation on your equipment and your with your crew members?
I can answer about crew members. We were planning to have, as I said, a habitat made of Vectran, which would be an anti-radiation fabric. And then on top of that, there's some new technology being developed of yarn with boron nitride nanotubes woven into it that's supposed to be used as an anti-radiation fabric. So we're thinking that in the future that technology will have developed enough so that we can use it for the crew. I don't know if someone wants to answer about electronics.
So when is that? When is your mission? When did you say your mission was going to be?
I think it was the launch window is 2040 or.
Okay, 2040, And then you think that the new fabric will be on the market or available before then?
Yeah, we hope so. I think one of our hopes, the idea of the mission is that it would kickstart more technology being developed quicker in order to have the mission happen. And so it would actually help in general space travel and, increase as an industry.
Okay.
Can I just add a point to that? Sorry. We have a mining facility that we're hoping to do as well, which is like inflatable. I'm not sure what the radiation shielding in the material itself is, but from the heat melt compactor, we can create radiation tiles, which maybe we can incorporate into the equipment mining facility rather than the human one, because it's already existing in the human one.
Very good.
Very good. Thank you.
All right, we have time for one more question. Justin, Glenn, either of you want to pipe in?
Go ahead, Justin. You haven't asked one yet.
Might help if I actually had the mic down. Yeah. I was actually going to ask a follow-on to Rob's question. The radiation mitigation methods that you described all seemed designed around ambient radiation exposure conditions. Did y'all think about adverse events like solar flares or other sources of extremely elevated radiation or like a galactic cosmic radiation burst, things like that, where you might have a very high prompt dose of radiation to the crew?
I don't think we'd considered that, gone into it quite that deeply, simply because it wasn't something we had gotten that far into with our research. But it's definitely something that we need to consider more.
So I've got a possible kind of thing. So the water, the percentage of it that is used for for electrolysis and what we use it for, we could use some of that for radiation shielding if there was an event in which there was a big solar flare or unexpected amounts of radiation, if that was necessary to protect the crew over I don't know, keeping some of the equipment intact, or so we could sacrifice some of the water to radiation shielding.
Okay.
That's a pretty good answer, actually. Good job.
All right, so that concludes our 15 minutes of Q&A. Francesco, any final words before we wrap up with the team?
Good job, guys. Presentation went very well. We're going to get together with our board of directors and decide about if your project will be funded or not. So you will probably know tomorrow.
All right. Well, thank you guys very much. I appreciate you guys coming and answering these questions. I'm very proud of the work you guys put in. You answered questions very eloquently, very educated. You should have heard me here. I was cheering you on. So good job, guys. I'm very proud of you. So Team Prometheus, thank you for your presentation. You guys may now leave, and we will stop the live stream on YouTube. So thank you for those that I watched. And have a great day, guys.
We'll see you at graduation tomorrow.
We will.
Congratulations.